Welcome back. Last time, we examined how to use NumPy's statistical functions and discussed why we prefer to use them instead of Python's native alternatives. This time, we're going to focus on functions about finding maximal and minimal values in an array. Without further ado, let's begin. We'll start by importing the NumPy package and defining a 2D array called matrix A. Since it's the exact same variable as before, we can simply paste the code from last time and run the cell. Superb! Next, we're going to examine the min function. It finds the lowest value of an array along a given axis. If no axis is specified, the function works on the flattened array, just like npmin does. To see it in practice, let's call npmin and plug in matrix A as an input. The output is 0, which means 0 should be the minimum of the flattened array. If we have a quick glance at matrix A above, we'll see that 0 is the lowest value, so the method works as intended. Of course, we can plug in only the second row just to make sure we're not misreading the output. The end result is 2, which supports our claim that the function operates properly. Great! The next function we want to look at is amin. The A here stands for array, meaning this function is specifically designed for working with arrays. The syntax is identical, so let's just call np.amin and provide matrix A as the input. Once again, the result is 0 because that's the lowest value in the flattened array. Hence, min and amin result in identical results. So we get two functions native to NumPy, which serve the same purpose and work with nd arrays. Additionally, min and amin produce the same results and take the same arguments. So how exactly are these two functions different? Well, they're not. Array min is just an alias for min, so the two are absolutely equivalent and interchangeable. So using either one is a matter of personal preference. Thus, we won't spend more time passing different values to the arguments or changing the input array, since the results will always match those of npmin. What we'll do instead is explore a similar but not too similar function called minimum. Unlike the previous two functions, minimum requires at least two input arrays. This is because it generates an array which holds the element-wise minimal values. In other words, the function compares the values at the same positions in each of the arrays before taking the lowest one and adding it to a new array. In this way, the output has the same shape as the inputs. To see it in action, we can call the function and plug in the first and the last rows of the 3x5 matrix. Hence, we write np.minimum, and in the parentheses, add the aforementioned arrays via indexing. The output array contains 5 values with the first 4 coming from the first row of matrix A, and the last one coming from the last row. This is because we're comparing the first element of the 2 rows and selecting the lower value. Then we move on to the second element, and so on. In our case, apart from the last one, the values of the first rows are lower, so we pick those, and the last value is from the third row of matrix A. There isn't a rule which dictates we only pick minima from one array, then from the other, and we can quickly see that if we compare the second and third rows. A minor change to the index of the first input is enough here, and the new output clearly shows how we're shifting back and forth between the two arrays. By the way, did you notice that I just said minima instead of minimum? To explain this, we need a bit of Latin here. We don't say several minimum values. Minimum is a Latin word, and its plural is minima. That's why we have several cases. If we need an adjective, we'd say minimal or maximal value. Alternatively, we can say the minimum or the maximum without the word value. Finally, when talking about the plural forms, we use minima and maxima. Great, let's get back on track. Even though the minimum function usually requires 2 array inputs, there is a way to circumvent this. If we reduce the inputs of a matrix, we can essentially pass all of its rows as inputs simultaneously. This is because we're essentially splitting it up into different arrays and feeding it to the function. The easiest way to do this is to just call the reduce method by adding .reduce between minimum and the inputs. The result shows the lowest values for each column of the matrix. Hence, this is the same as using min over the 0th axis. So, should we use reduce or axis equals 0? Well, the two expressions are equivalent, so using one or the other is a matter of personal preference. In the name of total transparency, you should know that the min function calls the minimum function, so using the latter is very slightly more efficient. However, since npmin allows us to call the function over other axes as well, it provides greater flexibility. That's why using it makes sense as well. Great job! After examining all the minimum functions, we also need to mention there exist maximum equivalents. The max, amax, and maximum functions work the exact same way as min, amin, and minimum, but provide the largest values in the array. Since their syntax is identical to the minimum functions, we won't spend any additional time exploring them here. But you can do that in exercises attached to this lecture. What we'll do next is shift our focus to the statistical order functions. In the next lecture, we'll examine how to find percentiles and quantiles, and explain the difference between the two. Thanks for watching.